Can you talk about why they simplify our wiring so much and why they're so much more flexible?
God, I really can, because man, I love these things.
Yeah, they're nice.
They make a wiring job so much easier.
Welcome to the HPA Tuned In podcast. I'm your host, Andre, and in this episode, we've got our very own Zac Perston joining us. Now, Zac is a ex-HPA employee. Wow, technically, he's still kind of on the books. He worked for us a couple of years ago and developed all of our wiring courses. That includes our wiring fundamentals course, our practical club level wiring course, and our practical professional motorsport wiring course. He then unfortunately got poached off us by the University of Canterbury, but every now and then they lend him back out to us, and since then he has developed our CAN course, and we've got him back in the studio at the moment developing and filming our PDM or power distribution module course. While he was here, we decided that we'd get him into the podcast studio and have a bit of a chat about his history, how he got into wiring, how he got involved with roading cars and developing the wiring harness for the defunct Lotus T125 project, just among other things. Zac has got an interesting background in that he has actually got an electronics engineering degree, and that's certainly not something you absolutely need if you want to get involved in motorsport wiring. But as we'll hear from Zac as we go through today's podcast, it certainly helped him out. We'll get his take on what level of training and knowledge that you would actually need if you want to make a career in the industry. Deep dive today as well on power distribution modules or power management units, PDMs, PDUs, PMUs, depending on exactly what brand you are talking about. Obviously, that's why we've got him back here in Queenstown at the moment. These are a product that's really become a lot more prominent in the enthusiast market over the last few years, where more manufacturers are coming online with these products and the price point is coming down. I believe that they are still a misunderstood product. First of all, we see a lot of people shying away from using them because they don't understand the benefits that they offer, and they are, as we'll find out in this podcast, significant. On top of that, there is also the price point. As I've mentioned, that's come down, but there's still a fair chunk of cash you're going to have to part with in order to purchase one. However, again, as we'll find out talking to Zac today, often that price point can be significantly offset by the time saving in actually building the wiring harness. So it's really important to actually factor in everything when you're making your decision. Most importantly though, even those people that I see who are running power distribution modules, they are seldom taking advantages of all of the advanced functionality and features that they offer. And that's again what we dive into really deep with Zac today as we go through our interview. Before we get into the interview, I just wanted to mention a post from our Instagram account. If you aren't following us on Instagram, please make sure you do so. We are HPA 101, and we're always punching out interesting and educational content. This one is in line with today's topic. It's about wiring, and specifically, it was actually from a lesson that Zac produced about branch points in your harness. And what we often see, particularly in professional motorsport wiring, is that these branch points are constructed and then concealed behind a heat molded transition or boot. Now, one of the things we often see here is that the wiring underneath these boots is covered in a special tape called Kapton tape, and this is the gold colored tape that you'll often see in this sort of harness construction. Now, that tape is there for a couple of reasons in our instance. Mainly, it's around protecting the underlying wires from the epoxy that is used at the transition points of these boots. And the reason we want to do that is that this way, if down the track the boot is going to need to be removed for a repair or something, maybe you need access to the wiring below it, that Kapton tape will prevent the epoxy from sticking to the wires, meaning that you can then unwrap the Kapton tape and you've got access to all of your wires. A couple of other advantages with the Kapton tape which make it work well in this application. One is it's very, very thin, so particularly when you recover down your DR25 sheathing, it's not going to give an unsightly lump underneath the harness. And you might be thinking, well, why is the look really important when you're talking about the reliability of a wiring harness? But it is. Aesthetically, we want to produce a really high-level product that looks great. So unsightly lumps underneath the DR25, something we want to avoid where possible. The other aspect of Kapton tape is it has a very high melting point. So this is important when we are using a heat gun to recover down those boots. We're not going to end up with that Kapton tape being damaged. Now, why I wanted to raise this is anytime we post up about Kapton tape, we inevitably get a couple of people that comment. There was a couple of fairly significant crashes involving airliners where Kapton was used, and this is brought up around the insulating properties of the Kapton tape. I just want to be clear, we are using Kapton tape in a very different application. First of all, the sort of voltages we deal with in the automotive world are very low compared to what is seen in the aerospace industry. So we're not comparing apples with apples here. The other aspect, as I mentioned there, we're not really using the Kapton tape as an insulation in terms of electrical insulation. So we're not comparing apples with apples here. I just want to clear that up because it is something that we do have raised from time to time. So remember, if you aren't following our Instagram account, make sure you do so, HPA 101. We're also really active in the comments if you do have any questions on any of our posts. For those who maybe haven't heard of High Performance Academy before, we are an online training school. So we specialize in teaching people how to build quality, reliable wiring harnesses. We also cover topics such as engine tuning, engine building, and race car setup and driver education. You can find our courses at hpacademy.com/courses. I just wanted to specifically talk today courses that are relevant to our topic of wiring here with Zac. We've got our wiring fundamentals course, our club level practical wiring course, and our professional wiring course. And as an added bonus, as a podcast listener, you can use the coupon code podcast75. That's going to get you $75 off the purchase of your very first HPA course, and we'll put a link in the description you can follow to find those courses if you are interested in learning more. All right, with our introduction out of the way, let's get into our interview with Zac now. All right, welcome to the podcast, Zac. It's not too often I've had the pleasure of having a person in the studio for these podcasts, but it's much nicer than doing it over the internet. So welcome along, and you're here at the moment filming an upcoming course on power distribution modules, power management units. We'll talk a little bit about that as we go through today's interview. But let's rewind the clock. You're no stranger to HPA. You've developed the wiring courses that we currently offer. And I'd just like to get a sense of how you got that knowledge. So can you give us maybe a bit of a quick history on your backstory, how you learned about automotive wiring or wiring in general?
Absolutely. It basically begins with me just being a horrific bogan. Always into cars, right? Like every project I did, it was always car related, car based. And I'm cheap. I hate paying for things, so I like doing stuff myself. So
Sure.
You pick up things, you learn things, building engines, drivetrains, and everybody's really afraid of wiring, so it costs a lot of money. So You learn to do it yourself and you figure it out. So that's what I did for a lot of modified streetcar applications for myself and friends. And then I started getting a bit serious about it and started getting really into electronics in general. And I thought, man, I should really get some professional, education behind me on this. So
Sure.
I decided university would be a good call. So I went to university and I did an electrical engineering degree, specializing in embedded electronic design. So a lot of coding,
Okay.
which was actually really useful when it comes to going back to working on cars, because you're always working with electronic modules. And it's always good to have a bit of an understanding about what's going on inside them. So I completed my degree. It was a pretty good time at university, probably too good at times. And went and I got a job working for a company just north of Christchurch called Road & Cars, which was interesting. It was really interesting. The story behind that is this guy running that company, his name's David Dicker, and he has a large amount of money, a very large amount of money, and he has a dream of building a supercar. So he's built this facility up there that is pretty intense. There's a lot of really good gear up there, including about 4.5 kilometers of paved full-on racetrack.
Yeah, I don't know a huge amount about Rodin cars, and probably those listening outside of New Zealand, it might not be a name it's got a lot of recognition just yet, but definitely I'd suggest Googling Rodin cars when you've got a moment, because there's some quite interesting stuff that they're doing there.
Yeah.
And it is kind of, it's borderline world-class facility that he's built there, right?
Yep, it's next level, and the facility that they're currently building that I think is going to be up and running, I think they're aiming for before the end of the year, is definitely world class. Like, it's a multi-million-dollar new building and all the machining facilities, and it's definitely pretty intense. While I was there at the very beginning of the project, David was offered an opportunity to purchase from Lotus their defunct T125 project.
Sure.
Which was Lotus's attempt to get extra Formula One testing time in about 2010, 2011, by basically building a car that, in theory, someone obviously very rich could purchase and run. So it's basically a Formula One car that someone could purchase. Slightly detuned engine, a little bit easier to run, you get way more hours out of them.
Yeah.
But chassis-wise and everything, it was all there for the era. But it did not go well for Lotus at all.
So what actually did go wrong? I heard about a few engine bay fires, but I don't know too much else about the T125.
So definitely not so well. I mean, it's a single-seater wings and slicks full-on race car, so not so much engine bay fires, but the cowling, like the whole rear cowling of the vehicle, designed basically far too close to the exhaust headers, and there's definitely plenty of cases of, when they were running them, of those catching on fire. When the container turned up with everything in there were a few engine cowlings that had obviously suffered. The main problem, I think, with it, though, was that they were aiming it for extremely rich people, right? It was an expensive thing. I think it was £1 million to buy the car, but you were also locked into a racing series, and a nutritionist, and a driving instructor, and all this was, I think, pretty locked down time frame wise.
If I remember rightly, you never actually took delivery of the car either, did you? They just turned up to the track with the cars and the transporter, and you rocked up probably in your helicopter, I guess, or your private jet with your race suit and your helmet, and that was that.
Yeah, which sounds great in theory, right? But being locked into a time frame around these things, like, anyone with that sort of wealth is, probably wanting to be pretty flexible in what they can do. So anyway, it didn't go well for them. I think they sold one, maybe two, depending on who you talk to. And then the rest just sat. I think they had 10 monocoque chassis built. They were done by HP Composites over in Italy. And they had Cosworth GP-V8 engines, gearboxes, and everything for theoretically all of these cars. And they said, "Hey, David, do you want to buy it? You've got a few Lotuses, we know you." And he said, "Yeah, sure." I had no idea what the price was, but I suspect it
probably not cheap.
Not cheap. So all that stuff turned up in a container, and it was pretty epic. Like, I had built some reasonably nice wiring harnesses before this, but as soon as the container turned up, a client got in contact and said, "Hey, I want to purchase one of these cars." And so we had to build one. And there was essentially a complete car there. Like, it was all assembled and painted and everything. It looked lovely. But it had no plumbing and no wiring and actually no electrical system at all in it.
Right. So these definitely weren't complete cars.
No.
Okay.
Yep. So
you're chucked in the deep end trying to figure out where to connect the wires to.
Basically, pretty much the deep end on that. So that was my introduction to working with really high-level race-grade electronics. So Pectel SQ6M ECUs, Pectel loggers. I think in the end, I specified we ended up going with a Life Racing PDM on them, just because I think someone had a contact with the UK over there, and we got a reasonable price on them. But it was a pretty full-on project to install all that and configure everything and wire it. We did have engine tune files for the SQ6Ms. Like, they came pre-tuned. So that was, like, obviously made things much easier, because tuning a Cosworth GP-V8 engine at that caliber is not something I'm particularly feel confident in.
Yeah, that would be deeper in the deep end. All right, so you've talked about a bunch of stuff there, and it was a very brief recap of your sort of education and history, and I just want to go back and unpack a few things there. So first of all, you said basically before you got into the university degree side of things that you'd sort of jumped into these wiring jobs, which I 100% agree. I think a lot of enthusiasts get scared of and kind of either put off, don't touch it all, or whatever it is. What was it that why was that different for you? Why were you comfortable of getting stuck in and figuring it out for yourself?
I think possibly just because I'm a massive nerd.
Bogan nerd, that's a combination.
Nerd. It's weird, right? I'll be sitting there playing some sweet World of Warcraft and then go out and do some skids. I mean, who knows? So big nerd. So I've always been into the tech side of things.
Sure.
So wiring, like computers in general and wiring didn't really scare me.
Yeah, okay.
So I figured if other people are doing this, I can probably figure it out.
Yeah.
And it took a bit of time, and finding reliable sources for information was really tricky. You'll read a bunch of forum posts and you'll be told 17 different things, and what do you read? And it basically came down to me for just trying stuff, trial and error, like have an actual think about it. Don't try and read a forum post and follow a set of instructions without understanding why that set of instructions exists.
I think that's probably a really good point that goes for just about everything in the performance automotive world. The information is out there, and the problem is sorting fact from fiction. But then, as you've just mentioned as well, I think rather than just blindly following instructions that someone else has mentioned that may or may not be entirely factual, if you actually understand the principles, the operating principles behind whatever it is you're dealing with, whether it's wiring, tuning, or engine building, that's going to put you ahead of the game, I think, compared to others that are just blindly following a path.
Yep, 100%. Absolutely couldn't agree more. And one thing I've noticed with dealing with a few race teams and working in the industry for a bit is if you are having a conversation with someone that is absolutely top tier in their field and really knows their shit and what they're doing, they'll let you know what they're doing. They'll talk about what they're doing, and they'll do it with confidence and authority. But if you walk in somewhere and there's the guy over in the corner and they're like, he does our wiring, and he just does it in a room by himself, and he won't share anything about what he's doing, and he's super secretive.
Yeah, that says a lot, doesn't it?
It's a real red flag trigger for me, because I don't know, you should always be trying to learn the new thing.
Yep.
And like share that knowledge around. It might just be me. I don't know.
I agree. I've said this before in the podcast, but it's why I still like what I do. I love what I do, I should say, really, is that you never stop learning. And I think as soon as you've got that attitude that you know enough or know it all, that's kind of where the wheels start falling off, in my opinion. So open-mindedness. And I mean, pretty much what you're saying there with the secrecy, we see this so much in the tuning world, and a hot topic of debate I see on the internet, slightly off topic here, but it's a pet peeve of mine, is tuners who lock their tunes, files.
Yeah.
And there's those who will argue intellectual property, and honestly, I call bullshit. The number of locked files that I've seen, and you don't need to see the tune. You run the car on the dyno, and you're like, this is just garbage.
Why does your timing jump from 10 degrees to 20 degrees? Nothing.
You know that deep down, the reason that tune file is locked is because the tuner doesn't understand what they're doing, and they're embarrassed basically for others to see it. So I think that secrecy thing, you're right, it does speak volumes.
Yep, definitely a trigger point for me that you see an awful lot as well. You should learn the thing and then teach the thing, so you don't have to do that thing and you can go learn the next new thing.
Yeah. All right, so your path though has been a little bit different to most that get into the automotive performance world, in that you went and did a degree. Do you feel like that is essential? Is sort of higher education really an essential, in your opinion, to be successful in the automotive performance industry?
I would say 100% no.
Okay, good.
Yeah.
Because I don't think a lot of our members maybe have done that, so that's reassuring.
No. I love the fact that I did a degree, and I genuinely use a lot of the knowledge that I got, because I still do a lot of embedded system development and coding.
Yeah, okay.
And
that's a bit beyond the scope of what we are normally doing in the automotive sense, though.
More than likely, yep.
Yeah.
Although, Motec build platform,
sure.
You get into it with that for sure. But no, I don't think it's essential to go to university to get into the performance automotive world at a higher level. What it is essential to do is work at it. take on projects, just do the work, and that's where you'll learn. And talk to people, make contacts, and like actually think about what you're doing. And be humble as well, and like don't get into the realm of you've learnt something and you assume that that's the only way that it can be done, and you know, a little bit of arrogance might form around that or something. But like, always be willing to take on that extra bit of knowledge that you just happen to see in an Instagram post or a Facebook post or someone you were talking to at a racetrack. And don't take it as a personal affront that someone's done something different to the way that you've done it. It's
I think it almost comes down to a bit of that Dunning-Kruger effect as well, when you're just learning and you kind of get that little level of knowledge and you sort of start feeling quite confident or maybe a bit cocky in your abilities. And then those are maybe a little bit further along the learning curve, you start to realise just how much you don't know. The old story, you don't know what you don't know when you're first getting started. And I think you're 100% right, and that goes again for all across the areas that I'm involved with, wiring, tuning and engine building. There's not a lot of black and white in the industry in general. There's some solid principles and foundations that we stick to regardless what we're doing. But yeah, I mean, there might be 5 separate ways of doing a particular task, and you might find learning from someone else that there's a faster or easier way or something that ends up looking neater when it's all done. So I think that is important to keep an open mind and never sort of, you know, disregard another option.
Definitely agree. Yep.
Now the other thing, just in terms of education, and this is something that we get a little bit of heat from. It's actually your fault.
Sorry.
There's an ad we run for our wiring courses where
I think I know where this is going.
There's an off-the-cuff comment that it wasn't meant in the way I think a few people have taken it, about you could trust your wiring job to your local auto electrician with a she'll be right attitude. Now, I think that was the exact statement. That's obviously triggered a few auto electricians out there. And we never meant to offend auto electricians, but I do stand by what you've said in a sense. I think, you know, the auto electrical world, auto electricians, the training that they do is really important and valuable. I would say that in general, there probably aren't a lot of auto electricians in the modern day, though, who would regularly wire in an aftermarket standalone ECU. And it's more these days about diagnostics. Not to say that they don't necessarily have those skills, but is that fair in your experience to sort of say that that's not maybe their main sort of bread and butter work these days?
Yeah, I would agree with that. I think definitely I remember exactly what I meant behind that comment, and I didn't imagine that it would be misconstrued at the time. I was referring to an auto electrician with a she'll be right attitude.
Exactly, yeah.
It's not all auto electricians. In fact, I hope it's like a couple of % of them out there, right?
Yeah.
Because as an auto electrician, you probably couldn't have that attitude. I mean, cars are so complex electrically these days, and doing the diagnostics on one can genuinely be quite frustrating.
Absolutely.
Like I follow a lot of YouTube channels where they, you know, repair cars and stuff, and watching that diagnosis process be followed through, it can get pretty intense. So the auto electricians with the she'll be right attitude probably aren't doing those jobs.
Yes.
And they're also probably not the people you want wiring your race car.
Yeah.
There's an auto, like I live in a pretty small town in North Canterbury, and there's an auto electrician down the road from me, and he regularly wires in aftermarket ECUs for a lot of pretty high level rally cars.
Yep.
And I've seen his work, and it's spot on, absolutely fit for purpose. They do a great job. But, you know, he's attentive and a lot of detail in what he does.
Yeah.
Charges for it as well.
Yeah.
But fair enough.
I think it just comes down to you can't sort of lump all professionals into one category and say outright, well, you know, that's they're not going to be able to do the job you need. That's obviously ridiculous. I just wanted to get some context around that, because I know that we've probably annoyed a large number of auto electricians, and that was definitely not the intent. Yep. But I think it's probably also fair to say where our wiring courses were born out of is the fact that the knowledge and the skills used, particularly if we look at the likes of the professional wiring course, or mil spec as it's probably more often referred to.
Race spec might be the term.
Race spec, yeah. Mil spec's probably chucked around with not a lot of actual understanding of what that term means, but I digress. So, you know, the skills and knowledge needed at that level you're not going to learn through your apprenticeship program as you're becoming an auto electrician. It's a very specific set of skills which we've tried to provide with the courses. So I just wanted to clear that up as well.
Yep, absolutely.
All right, so let's move on, and we'll talk a little bit more about this T125 project here. So again, I just wanted to catch up to speed there on some of that backstory. The T125, you've already mentioned, high-level race car with high-level electronics that we don't tend to see at the enthusiast level. So how did you even start? I mean, that's a potential nightmare even for someone who's relatively skilled in the industry. How do you even start that project on figuring out where to go with it?
I reached out to everyone I could think of that could possibly have had dealings with the project when it was being done by Lotus. And I did end up making a good contact at Cosworth or Pectel Electronics.
Okay.
So anybody out there that's listening that's worked with Cosworth Pectel Electronics can know that support is interesting.
Lacking is what we hear?
Lacking, it seems to be. But luckily, I managed to somehow find the email address of someone there that was pretty willing to help.
Right.
They did a bit of hunting and found a lot of the original documentation from the original designs of the car that had run.
Okay.
So that at least got me the pinouts for the ECU.
Yeah.
That and I had to send all of the ECUs back, and they unlocked them and then relocked them for us with our codes on them.
Okay.
And did the service and maintenance. I think I've got a battery in them that needs replacing as well.
Yeah.
Did that, updated their firmware, and when they came back, then I could look through all the configuration and I could see, how things were set up in there, and that helped me nail down pinouts and things as well. And from there, now I knew the pinout of the ECU, I could get into the real proper harness design.
Yeah.
So the ECU was set in stone, the logger was reasonably set in stone as well. We specified the power management unit, but I could, build the rest of the harness around that.
Okay.
And there were, because of the Cosworth GP-V8 engine, it's a full-on, professional, really high-level race engine. So a lot of things like the actual harnesses that go to the injectors and stuff, that's all inside the airboxes, and that's all pre-made by Cosworth and comes back to a junction box that mounts on the back of the motor.
So you're wiring to a junction box as opposed to every single sensor and actuator?
Yep.
Okay.
Yep.
That's going to make things a little bit easier.
Yep. And they managed to get me the wiring information on those as well, so I knew the pinouts of those junction boxes.
Yeah. Okay.
So that definitely made things easier from that perspective.
Yeah.
And we ended up carrying that through the rest of the car as well. The entire design was based around junction boxes. One at the front of the car for, a sensor breakout. A lot of it was sort of auxiliary sensors that may or may not be run during an actual race, but are definitely useful for setup purposes. And then a junction box at the back of the car as well. And
I think the thing that's we see these junction boxes. Anyone who's looked at a F1 car or basically anything at the professional motorsport level, WRC, Le Mans prototype, etc. That's generally the way. And what it does do, other than giving the ability to quickly and easily remove and replace a potentially faulty sensor or actuator, is it does give that potential for a little bit of sort of future-proofing. You could add sensors in that maybe weren't part of the initial loom into that junction box, which with a professional motorsport wiring harness is one of the downsides. Basically, once those are all heat shrunk and potted, not a lot of flexibility to change them, correct?
Pretty tricky job. Someone comes to you with a harness like that and says, hey, I just want to add in an extra connector here for a sensor, and you're like, cool, so that's going to require rebuilding a lot of this harness. Yeah, I'll get you a quote.
Yeah. I think that's the case that's so easy overlooked. And it doesn't matter if you're working at that level or just the sort of amateur club level car. The time spent in the planning stages and the documentation, quite often that's almost more than what we actually spend building the harness, and definitely pays dividends in the long run. Yep.
I reckon tenfold payback on that easy. I was just writing a little bit more for this power management course we're doing, and the quote that comes to mind is a project car ever really finished? In my experience, I'm terrible at this though, and the answer is no.
I agree.
Always wanting to make a modification and add in something extra, and if you can devise ways of making that happen down the line as easy as possible, oh yes, the dream.
We've just faced exactly that with our SR86, where I built, it actually helped with that, you built one of the sensor harnesses because we were in a bit of a time crunch, and basically the entire wiring harness for the engine and the sensors was built from scratch there, and trying to again future-proof that. I had an inkling that maybe somewhere down the line we might switch from the conventional lever actuated sequential gearbox to paddle shift. So we're smart enough to add in there some breakouts there for the up and down paddles, for the compressor, etc. But it's still very difficult to foresee every potential change that may be required down the track.
Yep, and in most race cars you'll absolutely see this, because there'll be a wiring harness running through the vehicle, and there'll be two other wiring harnesses cable tied to it as well.
Yeah.
And if it gets the job done and it's reliable, absolutely.
Yeah.
I'm all about it. But if we can work in flexibility,
you've got to be practical here as well. I mean, most of us aren't working with an unlimited budget, and while it'd be nice to then go ahead and remake that entire wiring harness, that's probably A, unnecessary, and B, potentially unfeasible cost-wise.
Yeah, definitely.
All right, so you've mentioned power management units, which was one of the topics I wanted to talk to you about today, because, as we've said, you're here filming a course on power management units, power distribution modules, PDMs, PMUs, PDUs. Take your pick of the acronym that you prefer. Let's get down to the nuts and bolts of that. What is this unit, and why do we care?
Cool. So I call them PMUs. It's just the lingo I've dropped into, so that's what I'll call it, a power management unit. So traditionally, we've got all these electronic modules in the car, and all the actuators, and radiator fans, and coolant pumps, and diff pumps, and all these things, and we need to give them power. We've got to turn them on and off at different times. And traditionally we've done this with relays and fuses. We've got to have the fuses in there to protect our wiring harnesses in the cases of failures. So we've got relays and fuses, and for each of these things we need a discrete relay, and depending on what it's powering, possibly a couple of discrete fuses. There's, on every relay at least 4 connection points. On a fuse there's 2 connection points. Relays are still they're an electrically controlled mechanical switch, so there's still moving parts in there. And just everything builds up to just little bits of unreliability creeping in.
Sure.
And it might be fine for, when you first build it for the first wee while, but I don't think there's anyone in the performance car game out there that hasn't, had an electrical issue and traced it back to a dodgy relay.
Yes.
This used to work fine. Now it's a little bit intermittent, and that relay is getting a bit hot, and, she's clicking on and off when she shouldn't be, and it's just, a pain.
Yeah.
So power management units take all that power switching that we need to do to different things, move it into one module that looks a lot like a conventional sort of ECU that you might imagine, and does all of that switching with solid state electronics. So no more moving parts involved. It can switch things on and off much faster. And then it replaces the fuses by tracking the amount of current through each of its, we'll call them output channels, which is each of those solid state switches inside it. And you can specify now to say, hey, this output channel, according to my design, should only ever draw 5 amps. So I might set a current limit on there of, say, 8 amps. And if it ever draws more than that, I know something's wrong, turn it off.
So, we can do this. There's a couple of things I want to cover here. We can do this, obviously, with a conventional fuse. That's the job of the fuse, is to protect the circuit. And if there's a dead short or something's going pear-shaped and the current draw becomes excessive, the idea with the fuse is that the fuse will break or fail before we get to a point where excessive heat's generated and we end up with melted wires and smoke getting out, which no one wants.
Yeah, or even, there's plenty of vehicles that are burned to the ground.
Yeah, absolutely.
Wiring faults,
we can't understate the importance from a safety aspect of the fuse. No one really, knows potentially what could go wrong that requires that fusing in there. So it is critical. So you're talking here about the power management unit can electronically fuse the circuit, and obviously with a little bit more flexibility around, instead of having to choose from a 15 or a 20 amp fuse, you could choose 17.5 amps or whatever your heart desires. There's a few more advantages though in terms of that fusing compared to a mechanical fuse. So talk us through that.
One of the biggest advantages is, if your mechanical fuse blows, it's a mechanical action to replace that, right? You've got to physically remove it and put it back in. There's probably not going to be a race driver doing this when his car's just come to a halt on the side of the track.
Yeah.
the component that's caused the fuse to blow might be just having an intermittent failure. So we need to know about that. Sure, that's awesome, but it'd be really good if we could get that car back to the pits, maybe make a repair and get it back out for the rest of the session. Get some points if we can. So a PMU could let you do this because it can be configured to shut that circuit down when there's a problem, but then retry it a couple of seconds later.
Sure.
Maybe that fault has, cleared. It's not, it's cooled down just enough to be able to limp the car back to the pits. The driver could have, like a reset button on the steering wheel that he can easily reach when he's strapped into his harness, and that could reset the power system and re-engage it and hopefully get the car running again to get back to the pits. I mean, it's a similar story even for a modified road car, though. No one wants to be stuck on the side of the road with a blown 10-amp fuse, and you've got to walk, half an hour to the local parts store to get a replacement. If you can limp the car there, that's heaps better.
Yeah. Now, the other thing, you've got the flexibility around controlling the fusing current versus controlling the allowable amount of inrush current, which is a consideration for some electric fans, electric fuel pumps, just for a couple of examples. The compressor for our paddle shift is another great example where in steady state conditions it can draw 18 to 20 amps, which is quite a lot. But the inrush current, when it first switches on, can actually peak at 80 to 90 amps. So can you talk to us about what is that inrush current, why does that exist, and how can we allow for that with our power management unit? Where does the advantage come from that?
Cool. So inrush currents you deal with when you're turning the power on to typically an electromotive load, like something that has a motor in it, but also loads that have big capacitors in them as well.
Sure.
We don't see too many of those in the internal combustion engine world. They're more on the EV side of things, but that's a whole different topic. So electromotive loads, as you mentioned, things like radiator fans, your air compressor pump's actually a really good one because that'll have a pretty grunty DC motor in it. So when you first turn that on, that DC motor's not spinning. So to the power management unit, it kind of looks like a dead short to ground.
Right.
But as the current starts flowing through it, generate an magnetic field, the thing starts spinning. DC motors will then start generating a voltage that opposes the voltage applied to them, called back EMF, and that reduces the current going through them. So they're only going to have that inrush current for a small amount of time until they're spun up to speed. So the PMU
We're talking milliseconds here, right? Maybe half a second or something.
Like easily less than a second for basically all applications. So the PMU needs to know that that's going to happen because you're going to set that steady state current limit and it's going to be looking at that when it's up to speed. But when you first turn it on, the current is absolutely going to be higher than that limit. So usually on an output like that, there's driving something like that, there's a bit of filtering involved. It could be as simple as there just being a time delay, saying, hey, the current has to exceed the set limit for more than 2 seconds before I trip that. Some of them out there get into really complicated mathematical functions around filters, but it's got to know that inrush current is going to happen, and you've got to be able to set that up so that when you turn it on, it won't trip the current limit. And it'll let
Otherwise, if we didn't have that functionality, you'd actually have to set the steady state current to be above the inrush current, which in the example I just gave, if we're pulling a consistent 80 to 90 amps through that channel for the output for our compressor, we're going to have a serious problem. That wiring is not going to last.
So this is sort of in a conventional setup, you can think of this as being the difference between a fuse and a fusible link. So a fuse will blow very fast. A fusible link, often called a slow blow fuse, can actually handle current over its rated value for quite a bit of time. Like it could be 20 or 30 seconds before it heats up enough to actually separate inside.
Right.
And that's traditionally how electromotive loads like this were catered for. You'd have a fusible link and you'd have slightly larger than required wire actually being run to them. But fusible links have kind of gone by the wayside. They're not really, they're not really something I want to deal with anymore. They're kind of a pain in the bum, trying to find housings to house them nicely and in an aftermarket situation.
But ugly.
Yeah, definitely.
All right, so I want to just come back and give a real world example that we've just gone through as well with our own race car. When you mentioned the fact of reliability of relays, and I imagine a few people out there have used relays in the past are sort of thinking to themselves, well, no, they're actually fine. And there's 2 examples I'll give here. One was from my drag racing background, not specifically on my own car, and this was prior to the time where these power management units were at a price point where they were kind of within reach of the enthusiast market. These have been around in professional motorsport for a long time, but they had huge price tags. So in drag racing particularly, cars that run big tyres, tube frame chassis, etc., going into what's called tyre shake is a real problem. And particularly with more powerful cars, the likes of top fuel, top alcohol, that tyre shake is horrendously damaging to the components in the car. And those will actually shake relays out of holders, or shake, the vibration is so harsh that it will actually separate the contactors inside the relays as well. So a lot of those cars would actually hardwire with no relays to get around that, which is not a real appealing way of doing things. And it means then if you're switching things, you can't use light gauge wire and low current to switch an output. It all has to be rated to the current handling capability of whatever that circuit we're controlling, correct?
Yeah, absolutely. And you'll be into a big grunty switch as well, and like all that stuff's going to add up in weight too.
Exactly.
And just building a wiring harness with large gauge wire is so much harder than, everything's less flexible and you can't fit it through holes, and it's just a pain.
So I just wanted to highlight that is a real issue, and I mean obviously tyre shake's something that even drag racers are trying to avoid, but it can happen. And in those top fuel cars, tyre shake can be so bad it's actually been known to knock the driver unconscious. So this is no joke. At a less significant level than that, when we got the paddle shift set up into our SR86, we were under the pump time frame wise, and we didn't have the opportunity to set up the pressure sensor for the compressor at the time. There's a little pressure sensor in the accumulator. Well, actually, we had to add that. So the MME system we're running runs basically a pressure switch, and it comes equipped with a relay. So that's what we ran for testing in our first event. In qualifying at Highlands, after the first 3 laps, I unfortunately got a time on the board, it stopped changing gear, and that was because the relay was a little bit, how would you put it, haphazard in the way it sat in its little holder. So these are the reliability problems we do see with relays. Yes, I mean, they can be made to be relatively reliable, but obviously in a motorsport application, we want to remove any chance of failure where possible. So I just wanted to talk about those couple of scenarios that are real ones that do happen. Now, there are some other advantages with the power management units as well in terms of actually controlling the inputs and outputs, which I think is again something that's overlooked. So can you talk to us about the options there for controlling the different channels?
Yeah, so the way I like to think about this is with a traditional setup with relays and fuses, the control of when those relays switch is hardwired into the harness, like it's physically built into the harness with wires. Whereas when we move to a power management unit, we decouple the inputs from the outputs, and an input can come in and we can configure how that input is read, what level it needs to get above before it will trip some individual output. We can have multiple inputs required to turn on an individual output. And we do this all sort of thinking in terms of logical functions. So and, or, if, XOR, these functions. And you can build up really complex control strategies just from these simple building blocks.
Yep.
And you can get some pretty advanced functionality. And this goes for both race cars and road cars. Even things like controlling wiper motors. I've seen it asked a lot. Like you get people want to control a wiper motor, and it's not completely trivial for a 2-speed wiper motor.
No, you'd think it'd be simple, but it turns out to be a bit of a bigger task if you want it to function correctly, right?
Yeah, because it's got a DC motor in it, and you turn that thing on and some energy builds up in the magnetic field, and then you turn it off, and that energy actually dissipates for an appreciable amount of time, and that can cause the motor to run on further than you think it might. So you turn your windscreen wipers off, they get back to their park position, and then they sort of continue halfway back up the screen. That's probably not really what you want.
No.
So doing that with a PMU, and most factory cars will do this in a different way, but we can do it with a PMU where it actively brakes that motor, and that's BRAKE. when you turn it off, it will short the contacts of the motor together. All that energy is dissipated really quickly and safely inside the PMU, and it stops the motor almost to a dead stop exactly where it is. The easiest example to visualize about this, because most people have probably used a battery-powered electric drill, is when you're holding down the trigger on your battery-powered electric drill and then you let it go, that chuck stops almost instantly. And that's because the electronics inside there are actively braking the motor at that point.
Now, this is also why on a lot of PMUs there will be dedicated outputs if you want to run something like a windscreen wiper motor.
Yep. There's definitely for that reason. There is another reason for that as well, though, in that the most common wiper motor you'll deal with out there, this could be different for really modern stuff, but the most common type that I've dealt with is got 5 pins on it. It's got 2 pins that are basically a switch, and they get connected together when the motor is in its park position. And then it's got 1 ground, it's got a high-speed input and a low-speed input. And if you power up that high-speed input, just because of the way the brushes are arranged on the commutator and the motor, there'll actually be quite a high voltage generated on the low-speed input.
It actually acts like a generator.
It turns into a generator, yeah. And if you wire that up to just any sort of input on a PMU, it could possibly damage it. So you need to be sure that the output that's wired up to, particularly the low-speed winding on that, the low-speed brush on that motor is specified to be that. And usually it will be one specific pin because there's some extra electronics inside there and sort of load handling. And they won't want to put that on every output because it'll be expensive, right?
I mean, it always comes down to just read the manual, right? That's going to be explained. But
RTFM, yeah.
Yeah, that's it. Okay, so that's interesting, but in reality, probably not too many people are going to get too pumped up about controlling a windscreen wiper motor. It's a function we need, but it's hard to get excited about.
Yeah.
Let's talk about some of the cooler stuff that you can do with a power management unit, though. So, you're almost unlimited. It's just how clever you want to be and what inputs and outputs you've got. But one of the ones that I like the idea of is an anti-stall function. So could you talk through what that logic looks like? What is anti-stall for a start, and how would you implement that through a PMU?
Cool. So race car grid, I mean, I haven't done a lot of race car driving myself. Definitely never started from a grid, but it looks like a pretty intense place, right?
Yeah.
You're on there, you're pumped up, the engine's revving, those lights are counting down, then they go out, and you've got to get off the line cleanly. Whoops, I stalled the motor. That's a pretty not great situation to be in. It's really dangerous for you and other drivers. So you want to get that motor running again as quickly as possible. So maybe if we could build some sort of system to really help you get that motor running quickly again in a really simple way, that'd be great. So thinking about what the driver would be doing there, he's just stalled the motor, a little bit of a panic position. Maybe if all he really needs to do is depress the clutch pedal to, decouple the engine from the gearbox, and the motor will automatically try and restart for him.
Yep.
That'd be pretty cool.
Makes sense.
And we can absolutely achieve that with a PMU. So we'd have some logic set up that would be, we'd have a button that would enable or sort of disable this anti-stall feature, and we'd make sure that the driver knows that when he's getting on the grid, one of his checklist procedures that he needs to go through is to enable the anti-stall function. So there'd be some sort of indicator telling us that that's enabled. Then we'd have maybe an input set up looking at engine speed, and it would say, if the engine speed drops below, let's call it 300 RPM, because the engine will always idle higher than that. So if it's lower than that, it's probably in the process of stalling. And the driver has the clutch pedal depressed, then try and restart the motor. Probably have to put a little bit more thought into that, because when you're designing a function like this, you've always got to consider the edge cases, right? Because edge cases will always occur. No matter, they're at the bounds, you'll never see them, but no, you will. They'll happen, and you've got to cater for those, because any function you're designing like this that could automatically try and start an engine, that's a pretty big safety concern.
Definitely. There's a lot of things that could go wrong there.
So I'd definitely put something in there that would look at vehicle speed as well, and maybe have it auto-cancel that function once it sees vehicle speed over, I don't know, 20 kilometres an hour or something like that. So we could be pretty confident that he's gotten away from the line then. We'll cancel that auto-start feature and it automatically turns off. Something along those lines.
And I mean, this is just one example. In the PDM course that you're currently filming, we've got another one which would probably be a little bit more common, where you've got redundancy there for a fuel pump. So maybe you've got 2 fuel pumps, and if one of the fuel pumps is deemed to become faulty, then it can automatically switch to the reserve fuel pump. And all of this stuff, again, can be done seamlessly with the driver never even being aware of what's going on. Another thing could be maybe you've got an alternator that's on the way out, so your battery voltage is starting to drop low, and again, in a race application, maybe we want to shut off absolutely every current draw on that battery that isn't absolutely mission critical for getting the car back to the pit. So again, there's no limit here other than your own imagination and the inputs you've got control over, outputs you've got control over as to what you can do with them. And I think that's in my opinion, particularly for a race application, really one of the advantages that power management units give us. I want to also talk about the ways we can get these requests, I guess, for a function to come into the power management unit, because traditionally, if we're looking back at fuses and relays, we've got hardwired switches. Now we've got a lot of different ways we can request a function. So let's talk about, for example, if we want the ECU to turn on a fuel pump. So traditionally, how that would happen is we've got an auxiliary output from the ECU, which we would wire up to the low current side of a relay. So basically, the ECU will switch that relay to ground, and that will then pull in the high current side of the relay, which will then switch on the fuel pump. A lot of flexibility in how that might work with the power management unit. We've got the ability to run a switch input that the driver can control, a CAN keypad, we could use that same auxiliary wire from the ECU, or a CAN message. So can you go into each of those and give us a little bit of detail on what those look like, why we may choose one over the other?
Yeah, so starting off with that auxiliary wire, you could absolutely plumb that into the PMU, and it could just read the state of that wire and say, hey, is it high? Well, that I know I've been programmed that corresponds to the ECU wanting the fuel pump turned on, so I'm going to try and turn on the fuel pump. But, there could be other logic worked in there, like you've said, with a CAN keypad. So we could have a button on the keypad that if you press, it will turn the fuel pumps on regardless of what anything else is saying, because you might want that for some fuel pump out mode, or even just for testing that the fuel pumps are going. So you could have some logic built in there around those that will look at either of those signals and turn the fuel pump on. You could have the flip side of that, a fuel pump kill. No matter what the ECU is saying, don't turn on the fuel pumps. And that's the flexibility we get, particularly when we start integrating CAN bus into this. Because once again, it's a decoupling process again of having the inputs decoupled from the outputs. With CAN bus, the data that we're sending around is no longer restricted to individual wires representing one particular request or piece of data. It's just information on a network. So we can put whatever information we want on that network. So we can change and chop and change that over time. And the flexibility you get there is amazing.
So in the example there of our fuel pump request, rather than that being a physical wire from the ECU to the PMU, that message, that request could just be sent over the 2-wire CAN bus, along with hundreds of other potential messages.
Absolutely.
Okay. Coming back to the CAN keypad as well, because we've seen these, basically come to prominence. Basically, all of the PMU manufacturers and a lot of the aftermarket ECU manufacturers are now using them. Typical ones we see are the Greyhill and Blink Marine keypads. Can you talk about why they simplify our wiring so much and why they're so much more flexible?
God, I really can, because man, I love these things.
They're nice.
They make a wiring job so much easier. So a common one I've dealt with would be the Blink Marine 8-button keypad. And this gives you 8 pretty nice tactile buttons with changeable labels and stuff on them, and they light up different colors, so you can give different signals to the driver about what mode it's in. And to do that traditionally, you've got a single wire for every different color, a single wire for every switch. Do you have that switch? Is it a momentary button or a push and then a push to release button? Moving to a CAN bus keypad, I've got power, ground, CAN high, CAN low.
So 4 wires replacing what could have potentially been 16 or more.
Oh, easily more, I would think. Yeah, to a reasonably nice keypad.
And the other flexibility there is you can adjust and change the functionality as you see fit once that's wired up.
Yep. So initially I might only be using 6 of those buttons, and then we've added a diff pump to the car, and I want to be able to turn that on and off. To be honest, I'd probably do it automatically with the ECU, but then have an override button as well. So I can, throw that in there and program everything to read that request coming from the CAN keypad.
Yep.
And so all your changes are now being made with a laptop, as opposed to some wire cutters and strippers and crimpers and lots of time and crawling around cars.
Now, I think the other thing that a lot of people overlook, as I've sort of already referred to, the price of these units, obviously there's still a range depending on the manufacturer, but the price of them has come down dramatically over maybe the last 5 or 8 years, and they are affordable now, but they still can be a pretty big investment when you're looking at how to decide where to apportion your budget when you're building a project car. And the thing I really want to sort of clarify or make people aware of that is so easy to overlook, particularly if you are paying a professional, that auto electrician with a she'll be right attitude, there's a huge amount of time saving in using a power management unit versus wiring in fuses, relays and switches, correct? That can be time consuming.
100%, yep. Wiring in relays and fuses is the most labor intensive and time consuming part of building a wiring harness conventionally. So when you move to a PMU, it'll have a couple of automotive grade connectors on it, which will be could be exactly the same connectors as used on an ECU. So, chances are he's already got the tools in his kit to crimp all those, and just the time savings around building just those, 1 or 2 branches coming out of the harness to plug into the PMU, I really can't understate. I absolutely would say it's going to offset at least half the cost.
I don't think
what you're buying.
We're obviously not saying that it's going to overall be a cost saving, but I mean, if you're spending, let's say, $1,000 on a power management unit, as you say, you might end up saving yourself a few hundred in terms of the wiring expense and labor. And then obviously all of the other advantages that we've already talked about with the power management unit come into play.
Yep, definitely. I'm just a total fanboy, really. Like, to be honest, I've totally switched to using PMUs in projects. I wouldn't have done a project for a long time that used fuses and relays.
Yeah, once you've experienced it, it's pretty hard to go back. All right, so brings us on to our next topic, which might be a bit shorter because we're probably going to run out of time before too long. But we've used the term CAN here a couple of times. Can you let us know what that is? There you go.
God, I had to work it in there. Dad jokes. Excellent. So CAN, Controller Area Network, is what that's an acronym for, and it is just a networking protocol that has become used really widely in the automotive world. It was designed originally for the automotive world back in the really late 80s or early 90s by Bosch, I think.
So this is nothing new.
Nothing new. Yep. It's and because of that, it's really robust. Like it's evolved a few times over the years. There's been CAN 1, CAN 2.0A, 2.0B. So it has evolved, but it's really robust and well known, and so much so that it's used massively in industry as well. Like factories are run on CAN bus with signals being sent around everywhere to different machines and turning stuff on and off. So it is robust and mature, and it's really, really nice to work with.
Sure.
So physically, CAN bus has 2 wires, CAN high and CAN low.
Yep.
And the way that works is when something wants to send a message on the network, it's going to be made up with bits.
Yep.
And the way these bits are read that's the thing that's really mature and defined, is it's a defined protocol that this string of bits that are coming in means this, and that's the only thing it can mean. To physically send those bits on the CAN high line, it makes the voltage higher, and on the CAN low line, it makes the voltage lower.
Almost like there's a hint in the name.
Exactly, yeah. And then every device that's on the network, instead of looking at sort of the absolute voltage values on those wires, it looks at the difference between them.
So there's a noise rejection advantage in this, correct?
Yep. Yep, because if I've got some really noisy device that injects maybe some voltage level of noise onto those wires, because of the way we physically construct the bus, it'll get injected into both of those wires. But the difference between those voltage levels won't change because it'll inject the same voltage into both of them. So the signal will still get through nice and cleanly. So it's called common mode noise rejection, and it's used everywhere in electronics, and exactly because it works, it's just great. So I mentioned because of the way we physically construct the wiring harness.
Tell us about that.
That's we twist our CAN high and our CAN low wires together. This means that they'll always physically occupy basically the same space in the wiring harness, so they'll be exposed to the same level of radiated noise. So that's
key for that noise rejection.
Yep, absolutely. There's another noise rejection property we get from twisting those wires, and that's that there will actually be currents flowing in that network, and they'll be flowing in opposite directions in the CAN high and the CAN low wires, and because they're twisted together, the noise that those currents generate gets cancelled out as well. So it's just it's a win-win all round.
Yeah. All right. So big advantage from my perspective with the wiring is massive simplification, which we've already talked about with the PMU, and this sort of just goes even further. Massive simplification in the wiring, particularly between different modules, and we're seeing over the years this has become so prevalent in the aftermarket electronics world. So rather than sending, we gave the example of the fuel pump before. So maybe your ECU is going to be asking for fuel pump, maybe fan 1, fan 2, I don't know, probably half a dozen other different things that it's going to want to function using auxiliary output. So we could either wire up those 6 or 10 different outputs to those relays or the PMU, or in this case, all of those requests can be sent over that same 2-wire bus. Along with everything else, we haven't sort of touched on data logging from our PMU. We can data log all of that, and that again can be sent over the CAN bus. So a huge amount of flexibility and a huge amount of data can be sent across that. One of the things that I really can't state enough the importance of is the integrity of the data when it's being sent via CAN. So I'll liken this to, it wasn't that long ago, if you wanted to put a wideband controller in your car, that was an analog voltage output. So you physically had to hook it up to a sensor, 0 volt, and an analog voltage input to the ECU. And where that gets tricky is that it's scaled air fuel ratio, or lambda, on a 0 to 5 volt output, which is reliant on the fact that if the unit is sending out 1.25 volts, it's assuming that the ECU is seeing 1.25 volts. And we can get ground offsets that kind of end up making that maybe not the case. And then we get inaccuracies creeping in. Whereas when we're sending CAN messages, if we're sending out lambda 1.00, that is exactly what we'll be decoding, correct?
Yep, it's digital data, so you're not subject to those ground offset issues anymore. And the lambda controller is, as you've mentioned, it's an absolute example where I would say, 80% of wideband lambda controllers I've seen with an analog output, when compared to something with a digital output, you could be off by 0.1, 0.2 of a lambda in there. That's pretty massive. That's huge. I don't want to call out any specific manufacturers of wideband O2 sensor controllers.
No, let's not do that.
But some are definitely better than others.
I mean, there are wiring strategies we can incorporate that minimize the ground offsets, but in my experience at least, even doing everything by the book, we're still opening ourselves up for some potential error.
Yep, absolutely. It's just better to know, and particularly CAN bus lambda controllers have they've become once again far more available on the market in recent years, and the price is coming down on them all the time, and they let you work in a bunch of other stuff as well, like controlling a wideband O2 sensor isn't actually as simple as just turning on the heater element when you turn the ignition on. You really don't want to do that, actually. It's how you kill wideband O2 sensors. So maybe you only want to turn that heater on when the motor's running. So now via CAN, you can send a message back to the wideband controller that says, hey, the motor's running, heat up that sensor.
I think that's really critical, because wideband sensors, we know that they have had a bit of a checkered reputation with their life expectancy, and a lot of that actually does come down to exactly what you're saying there, the control strategy when the sensor's heated, and the last thing you really want to do is have that sensor nice and hot and then start the cold engine and end up with moisture basically being pumped through it. That's a quick way to destroy the sensor. Another couple of like neat little tricks that I like with the wideband controllers I deal with on CAN as well. I'm using pre-turbocharger individual cylinder lambda sensors on our SR86 race car, and the problem with doing so is that you are working in a high pressure atmosphere. The exhaust pressure can be as much as the boost pressure, if not more. And what's easy to overlook is the accuracy of the sensor output is affected by that pressure. So what we can do there is we're monitoring exhaust manifold pressure. We can send that exhaust manifold pressure from the Motec ECU into the Lambda controller via a CAN message, and then the controller internally will then compensate and send out what should then be an accurate Lambda value. So that's just one example. Probably the more prevalent or more important, I should say, is that if we're using the wideband sensor for closed loop fuel control in a race application, we want to be pretty certain that it's only working when that sensor is actually deemed to be operating properly. So again, it gives the ability for to and fro diagnostic information. So if the Lambda controller says that the sensor's bad, well, the ECU can shut down and ignore that and just go to open loop. So those are the sort of things we can do with CAN that I think have really expanded the range of what we can do. The other thing I wanted to talk about here is the flexibility now in using devices from multiple manufacturers, because again, this is a standardized communication protocol. So can you talk to us about how that works?
Yep, so CAN bus, and we'll talk about CAN 2.0B here because that's most commonly what's being used by the aftermarket automotive performance world at the moment, is totally standardized. Like, its rules are written and set in stone, and all the manufacturers have to obey those same rules. So this number of bits at the beginning of that message is the message identifier, and then you've got other fields in there, and then your data comes in this format, and because they all have to obey that, they can in theory all talk to one another. There's things you've got to get set right, like the speed all those bits are sent around at, but then once again, some aftermarket automotive manufacturers do this better than others, but having the flexibility to define that, hey, I've received this message of 8 bytes. The first 2 bytes of that I want you to read as a 16-bit value, because we've got 8 bits to a byte, and we're going to call that data type a signed integer. And okay, so then I'll be able to get a raw number coming in there, anywhere between negative 32,768 and 32,767, and then we apply some scaling to that, and that scaling is agreed on by both units, and then all of a sudden, hey, I've got this module sending exhaust gas temp to this module of a totally different brand, but they're talking to one another really nicely.
The benefit from my perspective that has given us over the last decade or so, 5 years, whatever it's been, is that now we're not so much limited to a specific brand of electronics. And I mean, we all have our brand loyalties, but we might not want to run the same ECU and dash combination, or maybe in the case of our SR86, we're running an ECU master power management unit, but Motec electronics for the ECU and dash. And again, these just integrate seamlessly via this CAN messaging. So a huge amount of flexibility in what we can run and how we can configure it.
Yep, absolutely.
Now, I know that CAN is something that is seen as being a little bit scary, maybe like the next sort of step in, beyond wiring, and a lot of people are put off. Is it something that's easy enough for people to get their head around? And where are the stumbling blocks do you see?
Yep, I absolutely think it's easy enough to get your head around. Yeah, definitely. As far as stumbling blocks go, the biggest one is that you're going to end up working with bits and bytes of data. So you need a little bit of understanding around what those terms mean. Yep. And I'm going to use a term here that might scare a few people, but I promise it's not that bad. A couple of terms are binary and hexadecimal. So they're different number bases. Yep. Like we, count in base 10 because we've got 10 fingers on our hands. Well, hopefully you still do, unless you're a machinist. But so binary is base 2 and hexadecimal is base 16, and these exist, they exist because they exist, but we use them because it's how computers talk. And at the end of the day, we're dealing with electronics, and it's all computer stuff. So you need a little bit of understanding around binary and hexadecimal and bits and bytes, and that's probably the biggest bugbear for anyone getting into
It's a different way of thinking if you haven't come from that background, right?
Yep, which is why in the course when we did that, I tried to put quite a bit of emphasis on that knowledge and tried to kind of introduce it in a reasonably gradual way with good graphics to describe things as well, and give some good examples in there of how those systems work, so you can get to grips with it.
I think the other thing that's important to kind of understand is like how most enthusiasts will be using a CAN bus, and I mean at one end of the spectrum we've got the likes of maybe John from John Reed Racing, who's reverse engineering current generation Lamborghinis and Audi R8s so that he can replicate all of the factory CAN messages to keep the rest of the electronic systems happy with an aftermarket ECU. Now that's a big job, and that requires some pretty specific knowledge, and it's going to take a lot of time. Then at the simple level, where a lot of enthusiasts will probably be, is more picking a CAN template that's already pre-programmed by the manufacturer from a drop-down menu and configuring the two things to be working at the same baud rate, communication speed. Happy days, you're kind of good to go. And then there's some sort of grey area in between. Is that sort of a fair assessment?
Yep, totally a fair assessment. So when I'm talking about bits and bytes and binary, that is probably more towards that more advanced side of it, because then you're going to be constructing your own messages and deciding how data is sent out. But all the manufacturers I'm not going to say, maybe most cases even, have already done this work for you. They've defined communication, like how all that data is going to be sent out, and then it literally is just selecting the right profile from a drop-down box. Often you'll find the ECU manufacturer will actually be pretty keen, if you've got an application that they don't currently cater for, they'll be pretty keen to get the information and get that application into their software for you, because other people are going to want it as well. And
basically makes the product appeal to a wider market. What I have seen is a few instances, I can't remember a specific brand, but a few instances where we've got an ECU communicating with a dash, you pick that drop-down menu selection for the template, and sometimes you'll still see like an occasional channel where maybe the scaling hasn't been quite right. That's easy enough to go and manipulate that existing template though, but again, a little bit of understanding around what's happening is useful. It's only when you start getting to the more complex stuff that actually starting to write your own communication templates is where it comes in. And of course, if anyone listening does want to dive deep into that CAN bus course is perfect for that. Obviously, that's exactly why you developed it.
That's why we made it.
And we'll drop a link in the show notes as well if people want to find out more about that course. Before we finish up, I just want to talk about the future of where we're going with the likes of CAN. As you mentioned, CAN itself is nothing new, and the automotive industry tends to work pretty quickly. So what is the current technology that we're seeing come out that's going to end up replacing or superseding CAN?
Cool. So an admission straight off the bat here is that I haven't unfortunately kept up with the absolute latest on this, because all of the work I'm doing ends up being around CAN 2.0B.
Sure.
But that being said, there's CAN FD, which I've had a little bit to do with. That is sort of the next evolution of the CAN protocol, and the FD stands for flexible data rate now. So in the traditional CAN 2.0B standard, you set the communication baud rate, and that's the number of bits that are going to be transmitted on the bus per second. So 1 megabit per second or 1 million bits per second would be a really common setting for that in the aftermarket automotive world. Now CAN FD you'll still have to set a base communication baud rate, and maybe someone could correct me on this if I'm not entirely correct, but this is my understanding. You've still got to set a base communication baud rate, and that's what it will transmit the first part of the message as. Included in that first part of the message is going to be the speed of the rest of the message. And that will be influenced by the amount of data in the rest of the message. And you can now transmit, I think, not just 8 bytes of data, but up to 64 bytes of data in a single message.
Right. So a huge amount of increase in the bandwidth of information you can send. Now, just talking about that, the transmit rate, the data rate, so why is that important? Why would we want to have different transmission rates?
So the faster the data rate gets, the less reliable it gets. So whenever you're switching a voltage level on a wire, it's got what's called a slope time, a rising slope and a falling slope. And that takes actual amount of time for that voltage level to rise up and fall back down. And it's affected by the length of the actual physical wires and various other things, like amount of capacitance on the line and all these effects. So the slower you make that speed, the smaller percentage of time you know that signal is going to be changing its voltage level. So it'll be at the fixed voltage levels for a longer amount of time. There's more time to read it and get a clear reading. How this affects us in the aftermarket automotive world is that basically the limit for 1 megabit, which is the fastest approved CAN 2.0 speed, the maximum length of your bus you want to keep to 30 meters or less, if possible.
Unlikely to be a problem in automotive sense.
Yeah, you could run up and down the car a couple of times with a bus that long. So you've got this, bus length might be 5 meters long, and then you've got the stubs that come off that go to the devices, and you want to keep those to 30 millimeters or 30 centimeters or less as well. Yeah, and if you obey those rules, and then there's things around termination resistors as well, which we of course cover in the course. It'll be pretty reliable up at that speed. For safety critical systems though, and this is what the OEMs do, they run a lower speed CAN bus. Just for headroom, right? Because it's a safety critical system. We want redundancy, and we want a factor of safety of 4 in there as opposed to 1.5 or something like that.
So, I mean, you're talking safety critical here. This would be common with communication from the likes of an ABS computer or maybe electric power steer, something we really want to know is going to work.
Yep, absolutely. Safety critical systems like that. Airbag, seatbelt control modules, things like that, all their diagnostic information. Will be at a lower speed. I've seen 125 kilobit used for this, but I've seen 250 kilobit used for it as well. Yeah,
and I think I'd say more often than not, at least in my experience, OEs tend to go with 500 kilobit as opposed to 1 megabit. Seems to be common in our aftermarket world.
Yep, that'd be fair. Yep.
All right, we're running a little bit long here, Zac, and I want to crack the whip and get you back into the studio filming to finish this PDM course. Yep. So I think we'll finish up there, but we do like to ask all our guests 2 final questions. The first of those is, I'm going to chuck you under the bus here actually. If you looking at where you're at in your career at this point, and you got stolen off us, I haven't even mentioned this, you got stolen off us by the University of Canterbury, so otherwise you'd probably still be happily working at HPA, but we punch you back occasionally, they lend you out.
Thank you for doing so.
If you were to go back in time and give some advice to a younger version of yourself that might help fast track your career, what would that advice be?
Do more projects and don't be afraid of, I can't swear on here probably, but don't be afraid of stuffing it up. I spent years and years paranoid about screwing anything up because what people were going to think, and it doesn't matter. Just do the project, learn the stuff. You learn more from mistakes than you do from a success. If you do a project first time and it works perfectly, that actually terrifies me. You want things to go wrong so you can figure it out and you've got a deeper understanding. I would still say go to university because that was, I found for me, very worthwhile. But definitely all of the knowledge I use in industry came from doing projects. So I got involved with Formula SAE at university, and that was massive. It was absolutely massive for me. And I would tell myself to get involved with that earlier. Sure. I definitely would. Push for the university to take it on. So,
I'm gutted that Massey University that I went to never had a Formula SAE team. It's something I still regret to this day as I went through uni. I think, and the people I've talked to and, seen where their careers have gone after Formula SAE, I mean, it just jumpstarts. And also the contacts you build, particularly if it's overseas with the bigger Formula SAE competitions. Incredible.
I've got one... this is really tooting my own horn here, but
someone's got to do it.
Someone has to. We went over in 2015 was my final year, and I think it's the only year they've ever gone over, and the car was just electrically not a problem.
Perfect.
There's a story told because a guest came in to view the Formula SAE competition, and he walked up to our pits, and we're all out there eating ice creams. And he goes, "Oh God, what's gone wrong? The car must be totally broken. You can't fix it because you're out here eating ice creams." And we're like, "No, man, she's mint. We're just,
nothing to do.
Yeah, nothing to do, nothing to fix." And that's pretty uncommon.
We know.
So I would say to the younger me and anyone out there listening that's at a university and loves electronics or anything around motorsport, get into Formula Student. It's such a good time. Yeah, it's a lot of work, and it's late nights, and it's hard work. So good. Yeah. So worthwhile.
Yeah, I'm jealous, incredibly jealous. All right, last question for today, Zac. If people are interested in maybe following your journey, you're on the social media? What do we got here? Do you stay away from that?
I'm old, remember?
Okay. Yeah, right.
Not that old. Somewhat old. I'm unfortunately not on the Instas. I should be, right?
Probably.
There's heaps of cool stuff on there. But you can hit me up on Facebook. I mean, my name's all over the HP Academy site, Zac Perston.
Absolutely.
There's various Facebook groups that I pop up in from time to time, and show pictures of what I'm working on. So the Motorsport Wiring Alliance is a good one. Quite like that one. So hit me up on there, and we'll have a yarn about some motorsport stuff.
All right. Thanks heaps for your time, Zac.
Cool. Thanks for having me.
All right, that concludes our interview. And before we sign off, I just wanted to mention, for anyone who's been perhaps hiding under a rock and hasn't heard of High Performance Academy before, we are an online training school, and we specialize in teaching a range of performance automotive topics, everything from engine tuning and engine building through to wiring, car suspension and wheel alignment, data analysis, and race driver education. Now, remember, you've got that coupon code. You can use podcast75 at the checkout to get $75 off the purchase of your first course. You'll find our full course list at hpacademy.com/courses. Important to mention that when you purchase a course from us, that course is yours for life as well. It never expires. You can rewatch the course as many times as you like, whenever you like. The purchase of a course will also give you 3 months of access to our Gold membership. That gives you access to our private members only forum, which is the perfect place to get answers to your specific questions. You'll also get access to our regular weekly members webinars, which is where we touch on a particular topic in the performance automotive realm. We dive into that topic for about an hour. If you can watch live, you can ask questions and get answers in real time. If the time zones don't work for you, that's fine too. You're going to get access as a Gold member to our previous webinar archive. We've got close to 300 hours of existing content in that archive. It is an absolute goldmine. So remember that coupon code podcast75. Check out our course list at hpacademy.com/courses.